So, in today's section, we're going to start looking at functions of time. And the variables we're referring to are displacement, velocity, and acceleration. So, some of our kinematic or SUVAT variables can be expressed as functions of time. When will this happen? If we start with velocity time graphs, we're used to velocity time graphs that demonstrate individual, discrete sections of a journey that either have constant acceleration or no acceleration. So these have been straight line segments to make the velocity time graph. But actually, there are some situations and some scenarios where straight lines don't represent what's happening correctly. We might need to use curves to demonstrate how the velocity is changing over time, to demonstrate how the displacement is changing over time. In these cases, the velocity or the variable can be represented as a function of time. So it can be represented in terms of t. So here on the screen, this means that the variable is constantly changing. It's constantly changing dependent on the value of t. So we have variable displacement, variable velocity, and variable acceleration. Some of the key differences that you will notice: for constant acceleration, we have straight line segments. For variable acceleration, we have curves. For constant acceleration, we have gradients that we can calculate that are constant throughout each segment of the journey. For variable acceleration, we have changing gradients. We have a curve, which we know from pure maths means the gradient is constantly changing from one value to the next. With constant acceleration, we have our SUVAT equations, which we can make use of. For variable acceleration, we're going to start to use calculus. Constant acceleration, your variables are given to you as numbers, and for variable acceleration, the variables are actually in terms of t. So that's exactly what we're referring to when we say functions of time. Well, let's see this in action and look at an example. So here we've been told that a body moves in a straight line such that its velocity at time t is given by this equation. V equals 2t squared minus 16t plus 24. We're asked firstly to find the initial velocity. Okay, so I hope in the wording here you're going to pick up on the nuance. The initial velocity. Just the word initial lets us know we're thinking about the very beginning of the journey. This is when time equals 0. No time has elapsed, so t equals 0. So we're going to go ahead and substitute t equals 0 to find that velocity. T equaling 0 on a function is going to be the same as the y-intercept or the vertical intercept. So we should be able to see this by inspection, that velocity equals 24. That's the initial velocity of this body during its journey. Part B, the value of t when the body is instantaneously at rest. So when the body is at rest for just an instant, for a split second, it's at rest. This is a situation that we've come across before, but maybe you haven't heard this phrase linked to the situation. When we throw a ball into the air, it has positive velocity while it's moving up. It gets to a point, the highest point of its flight path, where it has a 0 velocity, and then it starts to have a negative velocity as it comes back towards the ground. That point, when it was just changing directions, when it was neither going up nor down, that is the instantaneously at rest. That's the point that we modeled where v equals 0. So whether a particle is moving vertically or horizontally, when it changes direction or where its velocity comes down to 0, that's what we mean when we say instantaneously at rest. So we can say that when v equals 0, what are the values of t that satisfy this? That gives us a quadratic that we can just solve. First, I'll actually divide through by 2 or factorize out the 2, giving me something I can do in my head a little bit easier. Okay, so I can see this goes into the brackets. We're going to need -2 and -6. So if these are the brackets, then we solve to get time is 2 seconds or time is 6 seconds. So there are 2 times when this body will be instantaneously at rest, after 2 seconds and after 6 seconds. Part C of the question says the value of t. We need to find the value of t when the velocity is 64. So we're going to set this velocity function. Let's just go ahead and set it equal to 64. So we get 2t squared minus 16t plus 24 equals 64. Okay, let's just rearrange to solve. So this is going to be minus 40. And once again, I can divide through by 2 to see if I can do this in my head rather than with a calculator. And I can see, yes, this is going to factorize. I'm going to get t plus 2 and t minus 10. So we have a velocity of 64 either 2 seconds before we start or 10 seconds after we start. So the negative 2 isn't going to make sense in this context. We're not interested in anything that happened before the journey started. So we'll discount that solution, and we're looking after 10 seconds, we'll have a velocity of 64. The last bit of the question, it asks, when are we going to have the greatest speed of the body in the interval? So let's not forget, speed is a scalar while velocity was a vector. So we need to check both directions of the velocity. The greatest magnitude of velocity is what we should be looking for. A sketch is going to help here. So here we have the velocity function. We know that it has roots at 2 and 6. And its greatest velocity is either going to be here or here. The interval we're interested in is 2 to 5. So these are the places where it's furthest away from 0. These are the places with the greatest magnitude in between t equals 0 and t equals 5. So I'm not going to rely on the sketch that I've made because I wasn't really thinking about the scale or any vertical scale. I only really was interested in the roots and the shape of the function. So I'll just substitute to double check which of these is going to be or have the greatest displacement, the greatest magnitude. So by symmetry, I know that this turning point is going to be when x equals 4. And obviously this is the vertical intercept, so that means x equals 0. So I'll check both of those two cases. So when t equals 0, v is going to equal 24. We knew that already. When t equals 4, v is going to equal, we'll just substitute into that function. And we get an answer of negative 8. Okay, so I'm really interested in just the magnitude of both of these. 24 versus 8. 24 is the greater speed, and that's what the question wanted us to find. At what time was this moving with its greatest speed? And that's between 0 and 5 seconds. So that greatest speed was right at the beginning of the journey. In this question, we've been given the displacement function. So s equals 2t cubed minus 3t. We've been asked to find the displacement after 2 seconds. So we'll just substitute t equals 2. And that gives us 16 minus 6, or 10. So there's 10 meter displacement after 2 seconds. It's 10 meters away from its starting point. How about the time when it returns to its starting point? We don't know what time that happens, we don't know the velocity, but we do know its displacement is going to be 0. So returning to its starting point indicates s should equal 0. So when s equals 0, we just have a cubic equation to solve. So we'll set the function equal to 0. I can see here that factorizing will be my first step. And these are quite easy to solve. First I get t equals 0 as a result. Well, obviously it was at the beginning of the journey when time equaled 0. The journey had yet to begin. So yes, the particle was at the start position. That's not the one that we're interested in. We're interested in the next time that it got back to its starting point. The next time its displacement was 0. Okay, so solving the expression in the bracket, we get t equals root 1.5 or root 3 over 2. which equals 1.224.